In this problem, uh, we have to calculate the angular velocity of the system when this point mass, you can see here in red color, collides with this vertical rod and sticks to it. So the entire system will rotate with some angular velocity after the collision. So that we need to find out. So we can solve this kind of problem using conservation of angular momentum. So you have to think about why the angular momentum is conserved in this case. So you can see the velocity of this point mass making an angle 30 degree with the horizontal. So there are two components of this velocity. See, the horizontal component is v cos theta and the vertical component is v sin theta, right? So this angle is theta. So this component of velocity v cos theta rotate this rod. Let's say just after the collision the angular velocity is omega. Okay, so initial angular momentum is nothing but, let's say Li is nothing but due to this point mass m v cos theta into L, right? And the angular momentum due to this vertical component of velocity is 0. So it's very clear. So the final angular momentum of the system when this point mass sticks with this rod and the entire system, rod as well as the point mass, rotate with some angular velocity omega. I can write the angular momentum due to the point mass is m v, let's say the velocity of the point mass is vf into L. So this is the angular momentum of the point mass. So we can put a point mass nomenclature of is mp here, mp. Similarly, the angular momentum of rod is mr half 1 by 3 mr L square. This is the moment of inertia of the rod about this point, let's say O pivoted, and omega. Okay, so in this case there are two unknown quantity, the velocity vf and omega. So there is a relation between bf and omega is omega L. Okay, let's call this omega f. So it's very clear, the velocity of the point mass is nothing but omega f into L, because it is sticks at the end of this rod. So you can put this value here, bf is nothing but omega f into L, and by conservation of angular momentum Li is equal to Lf. So equate these two equations, and there is one unknown quantity omega f. It is very clear. So you can get the expression of omega f is mp v cos theta divided by mp plus 1 by 3 mr into L. Okay, so if you put all the values, numerical values, in this expression, because you know mp mass of point mass and velocity, also initial velocity theta and rod mass as well as length, so you will get omega f is under root 3 radian per second. So out of these four options, option A is correct.